Okay, so good morning, and we will continue our study of phase transitions in simple fluids. And so one of the thing which we want to understand is the phase diagram of a simple fluid. Okay, I want to discuss that, and so I think I drew something before, but we'll get some more details of that. Okay, this looks better. P versus T. Okay, so there's a triple point, and then we did something like this, critical point, and then we drew something like this and something like this. And so this was solid, and this was liquid, I guess. But what is this? This is solid. This is liquid, right? And this is gas. These are the three phases, and this, as we argued, this will go off to infinity. Okay. So today, so on, you can pick any particular line. So for instance, let's pick up this line. I'll draw a yellow line close to it. It's supposed to be on top of it. So this is a coexistence curve. Okay. So at this, what are the phases which coexist on this line?
Liquid and gas.
Liquid and gas, right? So they can both simultaneously be there. And so the question to ask is, what is the slope? Okay. So how do we go about computing that? So we'll do that now. Okay. So let us determine that. Okay. And for that, I need some inputs. And so what we will do is that. So let's do some formulae. So we'll assume that we'll call the phases. One and two. Okay. So now, and they coexist on this curve. And so how are we going to do this? So this first thing is we will derive something called the Gibbs-Duhem relation, and then relation or equation, and then from that it is straightforward. Okay. So let's do that. And so if you recall, F is the Gibbs is the Helmholtz free energy, and that's equal to U minus ds. We had proved this in this thing, and we also know from the first law df. What is df from the first law? Minus s dt
minus pdv
plus mu dn. Okay, but there is a second free energy, which is the Gibbs free energy, G, which is F. It's a Legendre transform, and it's F plus PV. Okay, then so exercise shows that G dG is equal to, if you push all these things through, S dt minus V dP, rather plus V dP plus mu dN. Okay, so looking at this, see, we can see that G is a function of T, P, and N. Okay, so now let me motivate why I want the Gibbs free energy. So here in this phase diagram, the control variables are P and T. So the Helmholtz free energy is not the correct setup. So that's the reason you go to where pressure is something which you have. Okay, so G of Tpn. So this is what it's a function of these three variables, and so in particular, it's forget n for a moment. This is okay. Now, so then there's also like we how we got F equal to U minus Ts. From that also you can show many things, but you can also show that G G equal to okay is equal to summation over I equal to 1 to whatever, in this case 2 Ni mu I, where okay, so this is number of components or phases. Okay, and there'll be a chemical potential for gas. There'll be a chemical potential for all those things. So G, so we can also show this thing. So we have two equations. So this is so also here this will become summation mu I. Okay. I'm writing this way. So combining with the first law for multiple components. Okay, so we get dg equal to minus sdt plus vdp, sorry. Okay, so this is the thing, but we also have the above formula, but this is also equal to, taking this and taking d of this is also equal to summation over ni d mu I plus summation dni mu. Is this clear? So now we can see we can cancel the this term can cancel this, and so we get sorry, the things which cancel are different, right? This and this. Okay, so we have reached Gibbs to Hammond relation. So now on the coexistence curve, okay, one phase can convert to the other, right? Okay.
Sir, why didn't you directly equate that G and this G? What is these middle steps?
This step.
Yeah. So
No, this is, so there are two relations involving G. One is this, Let me number them maybe. This is relation 1. It's a differential relation. This is first law. And this is relation 2. Okay, so this is just relation 1 with for multiple components, and this is from relation 2.
Sir, how relation 1 has a summation over I?
Oh, I mean, I wrote above. So above, this formula was written for one component.
Okay, okay.
Okay. So if two components or vapor and liquid are in contact with each other, you know what will happen, right? So the temperatures will be equal in thermal equilibrium. Pressures will be equal, and then when they can go to each other in thermal equilibrium, what happens? What happens to the chemical potentials? The chemical potentials are equal. Okay, and so then d mu I, once equilibrium is achieved, mu1 will become, so mu1 will be equal to mu2. Further, d mu I will be 0 because it has achieved equilibrium. Okay, so the right hand side of this equation is 0. So now you can see we get minus. So actually I have to be a little bit more, I've been a little bit careless here also. I need to, yeah, sorry, I'll rewrite this equation. I wrote it. I should take care of all the components. So, yeah, G equal to summation over IGI if they are non-interacting. So that's what I have to write it. Okay, so what was that here? Sorry, minus SI dt. Temperature is the same. VI is also, this is the volume of the ith component. VI dP. Okay, plus mu I dN. Okay. Is this okay now? I mean, I made a mistake.
Yes, sir.
So SI is the entropy of this thing, etc., etc. Okay, so this is what we get.
Sir, while writing G, you said something about non-interacting. What was that?
Oh, so G equal to G1 plus G2. It means if there's no interaction piece, it need not be in general. There could be something which, when if there is some reaction happening, something, it could be something else. It could be lower than that. Okay,
Okay.
that's all. Not very deep. Okay, so now I have this. So again here, this is where I messed up. So I have to correct this also. Minus Vi. Okay.
It will be plus, right? Plus VIDP.
What?
The VIDP should be plus, right?
Yeah. Thank you. Okay. So this is 0. So we just get. So we obtain. I guess this is called the Gibbs-Duhem relation. So we obtain something. So we obtain, what do we obtain? We obtain no, actually I don't want to do this. I want to use a weaker relation. So I'll use something. So mu1 equal to mu2 implies d mu I equal to d Okay, so actually I don't want to use this. Actually, yeah, so for in fact for each component we have that thing holding, so let's just write it as, so where was the minus? Minus was with S, is it? There's nothing, they're just saying the change of the Gibbs potential. It's a version of the this thing. So I want to do this. Okay, so good. And so where SI is, okay, so this is a specific entropy, and VI is the volume divided by NI. Okay, so this is what we get. And so now since d mu1 equal to d mu2, whatever I wrote earlier is also correct, but I need something simpler. I need something simpler. I need something else. So that's what I'm doing. So d mu1 equal to d mu2. So I equate this. This implies minus S2 dt plus okay, so now we just collect terms. So we get, this implies dp by dt equal to dp by dt is equal to, so we put this here, I've got some sign issues I think, I don't know. No, I don't. Do I? I don't. Sorry. I- So this, so there are two phases, and so this gives you the slope. Okay, so now let's just try to decide what. So now what is S1 minus S2? Okay, let me be more this thing. I'll multiply it by t. The latent heat per particle. Right? It is proportional to that. It depends on the sign. Is this clear? Right? A dq, right? T delta S is delta Q. So if you want, say, water to go to steam, you need to supply that latent heat, right? Is that clear? Hmm? Okay.
Yes.
Okay. So we know something. So we can also work out the sign. I need to work out the sign of this thing. Okay. So let's say that now I will make choices now. So S gas minus SL liquid. This is greater than 0, right? Because to convert a liquid, we have to give that latent heat. Similarly, S liquid minus S solid is also greater than 0. Is that clear? So I'm fixing the signs now. What about the denominator? I want to work out the sign of the slope. Okay, so Vg minus VL, is it greater than 0 or less than 0? Let's ask a slightly different question. Which has higher density, liquid or gas? Which has higher density?
Liquid.
Liquid. So Vg is inverse of the density, so it will be the opposite, right? So Vg will be greater than. Okay. What about solid and liquid? Solid density of solid versus density of the liquid. Which one is higher?
Solid is high.
Okay. So again we'll have V liquid minus V solid is greater than 0, except for one material, which is anomalous. Water, right? Because ice floats on water. Okay, so what you can see here is that both numerator and denominator are the same sign. Okay, so implies dP by dt is greater than 0. This analysis for liquid gas, solid liquid, as well as, so 1 and 2 I have to choose, and we can go directly sublimation, right? Solid to gas. All these possibilities we get. Is this clear? Hello?
Yes, sir.
Okay. So now we can go back to our new this thing. We can look at this thing. So you can see all the curves have drawn with positive slope, but except for water. So let's use some other color and draw for water. So water, it should be something like this. For water, it should be negative. Okay. There's one more thing is that you can see one more feature you can see is that the liquid solid line is closer to vertical, and the reason is that the usually solids are a lot more denser than liquids, right? So the denominator of this formula, okay, will take much more will be much more smaller because the density difference is large. So the volume difference will be the inverse of those things. So that will become smaller, which means dP by dt will be larger. That means the slope will be steeper. Is that clear?
Yes, sir.
Okay. So now we understand why the liquid gas guy is less shallow compared to the liquid solid line. Okay. So also all these pictures fit in with this thing. So this is the so we understand at least the phase diagram with some more detail. Okay. So this is not a stat mech thing, but it's still something worth knowing. Okay. Okay, so now we will move on to, so this is what I wanted to say in general, and now we will move on to the Van der Waals gas. Okay, and so there are two curves which I want to draw. I'm having trouble drawing 90 degrees today. Okay, we'll accept whatever comes. Okay, so I want to draw the PV diagram for two cases. Okay, so and so let's do that, and let's make a different color. So, okay, so it's just that Van der Waals equation. We have drawn this thing, and so now a question to you is, on the left, is t less than tc or t greater than tc? The diagram on the left,
So there is no anomalous behavior, so
yeah,
it must be less than TC.
left one,
Yeah.
Greater than
greater
TC.
than tc, right?
Oh.
For t less than tc is when you should see the phase transition. You should see, okay, good. I'm not drawing the t equal to tc, right? So now, so the thing is, so if you wanted to do the Legendre transform to go from F to P, we have to do two things, right? We will add PV to it, and then we need to convert all occurrence of V, P becomes the independent variable. So here what we have is that if you give me a value of P, you will get a unique value of P. So it's invertible. You have only one solution, right? If you give me the volume for T greater than Tc, you get the pressure from the equation of state. Okay, but what happens here, right? So here let's take different things. So here it's invertible. You go further down also it's invertible, but if you take some intermediate value like this, okay, for a fixed value of P, we find that there are 1, 2, 3 solutions. Okay, so compare this with the magnetization story. Okay, so the analogy is exactly like that. So V is like N, okay, and P is like B, not the other way around, is it? No. The order parameter is V, etc. Okay, correct. Okay, so even there, when we try to do the self-consistent equations, we got 3 solutions, remember? So this is actually similar to that. I just want to point that out. So here, this is nothing great. Okay, so this is what is happening. And so now there is multi-valuedness. And so, but the resolution to this is that there are 2 phases. Okay, so something like, we'll say that this guy is, which is liquid and which is gas. So let's say this is VL and this will be V gas. Okay, and this is some unstable solution. Okay, so this is the analog in magnetization of up and down, right? All up. I mean, so this is a kind of, so you get, but here it is liquid and gas. Okay, so now the question is, and this curve has, as I pointed out, it has a region where, which is bad, and this is where things are unstable. Okay, so there is we have the Maxwell tie line construction. Okay, but it's not proven. It's just a statement. So, but it gives you. So once you do that thing, what you get is not that kind of curve. You get a different curve. It's like this. Then there's a horizontal line. Okay, so this is the corrected curve. This, okay, and so this line This is liquid. This component is gas. You can replay, okay, and this guy is the where they both phases coexist. Okay, so this is the proposal. So there will be some particular value of P. There will be some critical value P star where this happens. Okay, so this is the so you get rid of this thing by doing in this fashion, and Maxwell's stereo line construction says that this area and this area should be equal. Okay, but that's a much more scientific way of doing it. But at this point, I'll just pause here and ask if there are questions. Are there any questions or comments or something features you don't understand? Okay, so this would be the curve for t less than tc. Okay, so what I want to do is show you how to plot these various things, etc. So, but now, I mean, so how does the okay? So the thing is, what you do is that there are two phases. Okay, there are two phases, but actually, if you look carefully in this thing, there are 1, 2, 3 actually, 3 solutions, if you wish, for the B. Okay, and two phases, and so I won't say two, instead of saying two phases, I'll say there are multiple. Okay, for a given uh, okay, P should be not in this range, but once I'm assuming it's in one of the in this range. Okay, so when there are 3 solutions. Okay, if it is in this range, there is, or here, it's unique. Everything is liquid. Everything on the top guy, everything is gas, or other way around, whatever. Okay, so you get what I mean. Okay, there are multiple values of P for a given P. Okay, so we computed F, which was a F for the van der Waals gas. Okay, and now so what you have to do is, so when you, so F, so G, the Gibbs free energy, which is a function of P, V, and T. Okay, I'll not write this because you'll see in a moment why. This is equal to, okay, F plus PV, right? But now which value of V do we put? So I'll put an I here. Okay, there might be 3 solutions, so there'll be 3 components. Okay, so the idea here is choose min of G1, G2, G3 as the stable configuration. Okay, this is from stability. So if you have, it's like minimizing potential energy, right? If there are multiple solutions, you choose the one with the lowest energy. In this case, it's the lowest Gibbs free energy because P and T are our control variables. Okay, so this is what we want to do. And so what we have to do is to plot. So but the problem is that we have to do this Legendre transform. So the problem here is you substitute this Vi and then write it Vi as a function of P. And here also all the V's should be converted to P. You need to write, you have to do that inversion, and that is not. If you look at the free energy, it's not a simple formula. So we have to do it numerically. So I'll show you. I will do that numerically and show you how it looks. Okay, so let's just look at that. So let's come here. Okay, so just 1 second. Can you see my Mathematica notebook?
No, sir.
You can't? Okay, because I have to now change what I present to you. So just give me a second. Thank you. Okay. So you can see it now?
Yes, sir.
Good. Is it too small? I can increase the font size. Okay, I'll do that. Now you can see it, right?
Yes, sir.
Okay. So here I've just written G. This G here is G divided by N or whatever. But X here is the way, T is temperature. X is actually V, but we have to solve for V in terms of this. And I've converted everything to what are those reduced variables. Okay, so T by TC. Okay, so the variables are V by VC and P by, okay, so what is T by VC, P by PC. So they're all normalized. So you will not see any dimensionful quantities. And so in this notation, T equal to 1 is is the TC. Okay, so we just have to do plots. Okay, so what we have, so maybe I've done this somewhere else. So I'm doing variance. So this is just plotting. So if I say plot, so let's do this. Let me just enter this. Okay, so if I just go ahead and say plot T of X and say temperature below 1, which would be say 0.85. Okay. X from 0. Don't ask me what these numbers are. So 3, 4, 2, 3.5. Sometimes you have to play with it. Sorry, I need to change the plot range because it is. Okay, so you can see this, that there is, this is the curve that I had drawn. So you can see it's T less than TC. So you want to figure out what is the timeline. Okay, so this is for T by TC equal to 0.85. So it's less than TC. So we want to work out what is this red line. Okay, so what I do now is I will jump now and go to yes. Okay, so can you see this curve? Can you see my cursor?
Yes,
Yes.
sir.
And you can see this curve, right? So now you see here, so this is a curve of, so what I'm doing here is numerically I'm solving for G, where I solve, I invert P, I convert V to P. Okay, so I do that and I make V span through some values, and you see 3 lines now. Okay, one is like this, 2 and 3, and these are related to the fact that there are three values of V for a given in this region. There's 1, 2, and 3, right? So that's what we have. And so you see here that there are three guys. And so you can see here that what is the lowest value of G? I'll now trace. I come here, this is the lowest value. This is a point where now you can, and this guy you can see is, then I have to follow this guy. So there are two branches which go like this. And then, so one of them is say liquid, the other becomes gas. So phase 1 goes to phase 2. But there is a third solution which is sitting up here, which is always highest. And that is related to the fact that that's the unstable region. We know that, okay, from other computations. So now, so the correct way to do this is that you come here to this critical value. And so this is at 0.85. So I can actually ask this guy to give the coordinates. I say get coordinates and I come here. So it says that, so this is, by the way, this axis is P and this axis is T. Okay, x-axis is P by PC and y-axis is T. And G is negative. Okay, so that's why it's called negative. Okay, so this region is around 0.5. So this so the correct location for the tie line, according to this numerical solution, is 0.5, around 0.5. Okay, P by PC equal to 0.5. So is this picture clear? So this is a non-trivial diagram, but you have to do it numerically. Okay, you can't do it because it's you have to do this inversion. So I use something called nsolve, which solves some equation. Okay, so it lets me invert. And so this is, I've done the tie line construction for several things. The topmost guy is exactly T equal to TC. There's an inflection point. Okay, so you can see that these are the various tie lines which are there, but this is a key picture. Okay, so are you? I'll stop here so that you can ask questions about this picture.
Sir,
Yeah,
uh, from this, where the three curves are there intersecting,
yeah.
from this curve, how we are finding the location of the tie line?
Yeah. So now see, if you remember, I said that is G1, G2, and G3. Okay, so let's call this fellow G1. This line. There are three lines if you look carefully, right? One. This is G2. Okay, and then there is G3. Okay, and so the true Gibbs free energy is the minimum of these three at any point. So you take a value of P like this here. Go like this. Fix P here. Okay, so which is the lowest? This one. So this is the stable phase. You come here. Here you come. It intersects only one thing. So this is the stable phase. You come here now. You can see again there are three solutions, but this is the lowest. But this is the other phase. So what I'm saying is, you follow the lowest line. Okay, go from below. So I'm tracking the actual value of the Gibbs energy. Is this at this point the two phases have the same thing, and then after if we change P further, we go like this.
Okay. So
Okay.
their y-axis is
yeah. So the tie line is where they coexist. What is y-axis is temperature. Sorry. Yeah, it is temperature.
okay.
But that is kept fixed in this. What am I
So
plotting? I'm sorry. What am I plotting? It's just G versus P. Sorry, G versus P at fixed temperature. So y-axis is G. I said temperature, right? Wrong. Is G. G versus P for fixed T, which is less than TC, of course. Okay, and I've taken the values such that I see this part of the region. If I had taken some values which are, in this corner, you would have seen only one line because there is a unique solution. Okay, so you can see that three solutions exist only from this range to this range, which is kind of true, right? In this thing also, from here to here only it exists. Okay, it depends on the height of this. So this is the correct way to go about assigning the phases, etc. But the final picture is exactly what I drew. Okay. So let me go back to my,
So to construct the tie line, like, do we see that intersection point and construct a
yeah,
line
that's the only way.
deviate?
Yeah, that's the only way I one can do it. Okay. And Maxwell's construction saying equal areas is roughly correct. Okay.
Sir, in that figure, there are 3 points where the lines are
Intersecting. Yes.
intersecting. So,
1, 2, and 3. Yes.
yes, so all three corresponds to tie line, or
No, no. Here, this is not, because there is this line which is stable. So this is not. So this and this is meaning. Have no meaning. They are unstable. All these points, basically these points are unstable. This is unstable. This is not. If you put it here, it will just decay into this guy. If you put it somewhere else here, I mean, here it will come here. That's all. Okay. So the tie line is determined by the lowest value where these two things intersect, which is this point. Okay. So let me now go back to my tablet. Okay, is this clear? So I'm sorry, I have to do this numerically, and that's why I would suggest you do it also. It's, I mean, a lot of work went into making this thing work. Okay. So we saw the following picture, right? So I'll draw the picture now. P versus G. So we saw something like this, right? So okay. And now I can show you the stable guy is okay. So this is P star. Okay. So this is the conclusion. Okay. Now I leave it as an exercise for you to figure out which is liquid, which is gas. It's not very hard. So I'll stop here and pause for questions.
sir,
Yeah.
I have a question from that initial portion where we have written DGI, that portion. This, yes. So here we have for individual component we have written the expression, right?
Yeah.
So, but the previous expression there is a
Even that is correct, no? Because it's for the sum. It will also be correct.
okay. So with
Yeah. But I wanted to use the fact that d mu equal to 1 equal to d mu. That's why I put it
sir, then what is the need for the first equation?
there. Yeah, that is because I messed up. Yeah, you're right. That was not necessary.
Okay.
Yeah. I mean, it's like I'm doing things in my head and writing. So that's what the mistake was.
Okay.
Okay. It's my fault. Yeah. Unnecessary detour. Sorry.
Okay.
Yeah. Sorry about that. Okay. So let me just stop recording. Good question.